Hi everybody, welcome back to the Feynman technique. Today we're going to be doing something a little bit different. I'm going to be solving a problem in real time. I might pause the video to do some calculations. Now this integral where h is a real parameter, I tried to get various AIs to solve it as well as plugging it into Wolfram Alpha. I tried ChatGPT 3.0 Mini High, which is the best commercially available AI chatbot as far as solving complicated math problems is concerned. I also tried Grok 3 in think mode, and nothing was able to give the correct answer to this. So this has been like a topic that's been, it's fascinated me for a while. Like, what types of problems are humans still required for? And I guess this one is one of those, because I was not able to get an AI chatbot or Wolfram Alpha or online integral calculator to get the correct answer to this. I'm not saying that there isn't one that could do it maybe eventually with some help, but just putting this integral in there and then saying that h is a real parameter and to not evaluate it numerically and then guess, which sometimes they like to do. AI chatbots especially will evaluate it numerically and then try to find the closest closed form expression for it, and then just say that it's equal to that. But again, it was unable to do it. So we're going to be working on this together today. So I guess a technique that I've been doing lately is stating that the imaginary part of the natural log of an expression a plus bi is equal to the arctangent of b over a. All right, so let's try to match that up here. Well, let's identify our b. And in this case, our b, since we have arctangent, and we want to make this b over a. So we're going to let b equal h plus cosine x, and a is just going to be 1. All right, so this means that the imaginary part of, let's put in our a, that's 1, and then we'll put our b after the I. So that's the imaginary part of h plus cosine x. All right, so we know that's true. Okay, so this implies that oh, okay, sorry. And our b, I forgot to plug in our b, is h plus cosine x over 1, which is just h plus cosine x. And that's exactly what we have here. So now we can say that I is equal to the imaginary part of the integral from 0 to pi of this expression right here, integrated with respect to x dx. Okay. Let's put in some value for h. Let's let h equal e. Okay, so now you could see at h is equal to e, we have this expression. This is what the graph of I would look like for various values of h here. And if we zoom out, we can see that it's continuous from negative and from h equals negative infinity to infinity. All right, so where was I? That's right, I was right here. We're going to plug in a certain value for h. We'll let h equal, we'll let it equal 1 over e. And we'll do e squared plus 1, just to give it a really, really nasty value for h. Okay. So now let's go ahead and reparameterize this integral right here. All right. So we're going to let some f of t be equal to the integral from 0 to infinity Let me go down a little bit. Well, no, let's show as much of the work as we can. Of the natural log of 1 plus t h plus cosine x dx. It looks like it did not give us any sort of graph. Looks like this is only valid. Let's try some different values of h here. 1, 2. All right, did I make some sort of mistake here? Let's see. Imagine, yeah, that's right. And then so the imaginary part of the natural log of 1 plus I, or b is h plus cosine x is equal to arctangent of h plus cosine x. Yeah, so that should be right. Why? Oh, because I put in bounds of integration going to infinity. There we go. Let's put back in our nasty value for h. All right, let's do e squared divided by pi squared of just pi plus natural log 2. There we go. So that's a really nasty value. All right. All right, so there's our f of t, and it looks like our t is not going to be good for values of t less than some value, but we won't worry about that. We'll figure out what the restrictions on t are when we're done. All right, so since we're using Feynman's technique, as I always do, we're going to be taking the derivative of this function with respect to t. So now I'm going to write it as f1 of t. Just know that that means f prime of t. And it's going to be equal to the integral from 0 to pi of 1 over this thing right here times the derivative with respect to t of the inner function, which is just going to be h plus cosine x dx. All right, so there's our f prime of t. Now let's just make sure we did that right. So I'm just going to put a ddt in front of this and make sure the derivatives match up. And they do, it looks like, for t greater than some value. It looks like that whatever value that is depends on h. Okay. Okay. So there's f prime of t. And now what I'm going to do is I'm just going to go ahead and put this into the online integral calculator. We could solve this. I know this is solvable. Well, actually, it might not be solvable yet. Let's see if this is solvable in online integral calculator. So I'm going to copy this over here and then make a new tab in integralcalculator.com, put it in here, and we will integrate from 0 to pi dx. Go. This is a really good website, by the way. Okay. Yeah, it says it's pi over t, and I just don't believe that. I do not believe that's equal to pi over t, but we'll go ahead and check. All right, so let's do f of t equaling pi over t. No, not even close. Okay, so online integral calculator couldn't even do this. So let's rewrite f of t a little bit different. So f prime of t will now say is equal to this, and then we're going to modify it a little bit. Let's put a parentheses in front of here. And then we'll put a t here, and then a 1 over t. All right, so we have the exact same thing. All right, and then we're going to just go 1 plus. Well, if we did that, we'll have to subtract what we just added. So we just added this. So we subtract that, and that should get us back to our original f of t. All right, now you'll notice that the reason I did that was because this is just going to become dx now. So this is just going to be pi over t. All right. And now in, let's see. Let's expand this out a little bit. Let's say that this is th plus t cosine x. and then we can group them. And now we have a form of an integral that I developed a formula for. That is this formula right here, the integral from 0 to pi of 1 over a plus b cosine x dx. And we'll put in some values for a and b. Let's put 1.2 and 1.5. Oh, it's undefined. Oh, of course it is. Yeah. We need b to be less than that. Okay, so and that's going to be equal to pi over the square root of a squared minus b squared. Yeah, and let's make sure these things always match up. Yeah, that was the formula I developed. So we can say that this is true with certain restrictions. Obviously, we need this to be greater than 0. A squared minus b squared has to be greater than 0. All right. So let's apply this to our formula. That implies that our f prime of t is just going to be 1 over t times whatever this integral would evaluate to, with a being equal to 1 plus th and b being equal to t. So our a was again 1 plus th, and our b was just t. Yeah, and it looks like we got some other stuff in there. You can see, let me just match up these graphs right here. This was our original expression for f prime of t. And then if we actually got it here, so there must have been something else going on here. But it's still good for positive values of t. Okay, and hopefully other values too, like imaginary values too. Again, we'll clean it all up at the end. I just use this to make sure that I'm not getting too far off track with my work. All right, so now we want f of t. F of t is just going to be the antiderivative of this with respect to t. So we're going to get, well, the antiderivative of the first one is just going to be pi natural log t. And then minus the antiderivative of this with respect to t. Now I believe online integral calculator will handle this one. All right, so we're going to copy that, and you know what? It might indeed actually it might handle the whole thing. So let's just go ahead and paste that into the integral calculator, because with enough time, I could definitely evaluate that integral. I recognize that it is. We're taking the indefinite integral. It's definitely something I would be able to solve with enough time. It would just be a lot of work. All right, so we're going to use the calculator to do it. All right. All right, so it looks like I always like to use the manual integration one. Okay, so it looks like our f of t, or our f prime of t, evaluates to this. All right. So I can copy it over in LaTeX form, and it will actually paste right into Desmos when I do that. So f prime of t, or no, I'm sorry, f of t is equal to the antiderivative of f prime of t, which is equal to this. All right, let's see how close we are. What was our f of t? Yeah, okay, let's do a plus c, and then see if we can, yeah, that matches up very nicely for whatever value of c we're going to end up getting. All right, so let's see. If f of t is equal to this, then f of 0 is equal to 0. So we can say that f of 0 is equal to 0 and plug that in down here. So we can say that f of 0 equals 0, but it's also equal to this expression where t is 0. Okay, it doesn't look like we're going to be able to plug in t as 0 directly. So what we're going to want to do is clean this up a little bit. All right, so what I'm going to do is factor out a pi. let's get rid of that plus c for now. And we're going to factor out. There we go. All right. So let's factor out a pi. All right. Hold on a second. Let me recopy this. Yeah, I see what happened. I knew there was some sort of mistake here. All right. So by the integral calculator, our f of t is equal to this, plus c. So let's factor out a pi, and then use the properties of logarithms to bring this t inside this other natural log. Okay. So we're just going to put, all right, so t comes inside. This is just going to become a 1, and then we're going to get a t, and then we're going to get a t. All right. Let's bring this t inside the square root as a t squared. We're still good. All right, and then we can bring, oh, t squared. Yeah, there we go. All right, and then we can bring this t squared inside this parentheses as a t. So this is just going to become a 1 plus th. All right, there we go. Now let's make sure this still matches up. Yeah, that's going to fit. Okay. All right, now we can say f of 0 is equal to 0, and from here we can say that this is equal to, well, if t is 0, that's 0. If t is 0, that is 0. If t is 0, that is 0. This is going to be the square root of 1, which is just 1. This is 2. Rid of the absolute values. So 0 is equal to pi natural log 2 plus c, implying that c is negative pi natural log 2. All right, so our f of t is now minus pi natural log 2. Okay, well, I is equal to the imaginary part of f at I, right? I forgot to write that down, but, right, because this is our original I, and so I is the imaginary part of this, which is the imaginary part of this at t is equal to I. So, can also say that I is equal to the imaginary part of f evaluated at I. So let's copy this down here and then say what it actually is. Well, you'll notice that taking the imaginary part of f at I, this part's going to drop out. So we only need to copy this. So we're going to get pi times the imaginary part of this, where, and I'm going to get rid of the absolute values also. The imaginary part of this when t is equal to I. Okay. So I squared is going to give us a negative 1, so that's plus 1. And then that's going to be IH. Okay. So now is a good time to use the calculator again. I mean, we could figure out, we could extract the imaginary part of this. Again, it would be a lot of work. But you could totally do it. I mean, it's not undoable. It's just a lot of work and a lot of steps. So I'm going to go ahead and pause the video right now and find out what that is. All right, so I was able to get the answer, and actually I just typed it in to Google. It has an AI that's fairly competent at just calculations, and this is a calculation right here. This isn't anything. It's difficult. It's simple but not easy. The process for doing it is pretty simple, so I don't feel bad about plugging that into a calculator. But it gives you this. So the simplified expression is pi arctangent of h over, and let's see, let's test this. So we have I is equal to pi arctangent arctangent of, and then what's on top? H. It's H over, let's see, the square root of 1 minus H squared over 2. And then we're still inside the square root, but now we have another square root plus square root of 1 plus, and if this isn't right, I'll have to figure it out myself. 4 over 4. All right, what's that value? 3.28. Let's see, does that match? Oh, yes, it does. It matches it exactly. Now, let's just make sure. Let's plug in h is equal to 1, and then just slide it down. Oh, yeah. Yep. That is perfect. So that is the answer. All right, guys, that's my process for solving integrals. Before I present an integral, I usually like to make sure it can't just be plugged in to, one of the AI chatbots to give you an answer directly. For instance, oh gosh, Grok is still thinking. Oh no, this is mini high. It looks like it just crashed out. So let's see. What did Grok give me? Did Grok give me anything? Oh yeah, it gave me pi arctangent h. Yeah, I don't think so. Oh, looks like ChatGPT is done. Let's see if it got the right answer. I'm interested. We'll try pi arctangent h, but I'm sure that's not right. Pi arctangent h. I mean, it's close. And it probably guessed, just like I told it not to. And you can see where pi arctangent h is very, very close, but it's not exact like ours is. All right, let's see what... Did it get it? Okay, let's see if ChatGPT 3.0 mini high got it. All right, let's plug in arc sine of... We got a fraction here. The first one is the square root of h. I'm going to be mad if it got it. Squared. Oh no, it's h plus 1 squared. Plus 1 squared. Plus 1 minus square root of h minus 1 squared plus 1. And then over 2. No, that's complete. Let me make sure I put it in there correctly. Yeah. All right, good. I was hoping it would get it wrong. I take pride in, mathematicians still being necessary. All right. So, yeah, it looks like mathematicians are still necessary for this one. I did use calculators a lot of the way, but I was not simply able to plug that into a calculator and get the correct answer, which is, I'll plug it in. I wasn't able to plug this into a calculator and get the correct answer, which is this. You might be able to simplify that a little bit, but I mean, that's good enough. All right, guys. If you watched the whole thing, congratulations, and I appreciate it, and we will see you next time.